Hello everyone. Today we're going to have our second pre-recorded session. Today we're going to talk about turbulence modeling. Arguably this is going to be one of those difficult subjects that we will cover in our class, but as always I will try to make it as simple as possible. So, what's turbulence? The pure definition of it is an unsteady aperiodic motion in which all three velocities components fluctuate. So basically what this means is that if you have any sort of unsteady aperiodic motion in your velocities in your system, that is going to be called turbulence system. Now, there are two crucial parts to this definition. One is being unsteady, meaning it has to be time dependent, it has to be changing by time, and more importantly, it has to be aperiodic, meaning you cannot define any periodic function, any time setting, any time period that based on that time period of frequency you can predict the velocity. So it's totally unpredictable. So there is no per se tone to it, and it is totally without any frequency, one or a group of frequencies. This is very important because there are many unsteady flows in which the velocities fluctuates, but they are periodic, meaning that you can find a function and define frequencies that can basically predict your system. But in turbulence, that's not the case. Now, the effect of this unsteady aperiodic motion is mixing the momentum and energy in your system. Now, if we look at it, if we look at the velocity, and this considered U capital is our total velocity, and this is time on the horizontal axis, and your velocity on vertical axis. So if we look at it, the velocity is fluctuating and changing. So there are both local fluctuations and general changes in the velocity. You can basically decompose your velocity to two parts. One, the average velocity, meaning the average velocity as a straight line going with the general changes of the flow. Okay, so that's one thing. Let me see if I can draw here. Yes. So what I mean on this is that your average velocity would be something like this. So it will go up, come down, okay, like this. So that's your average velocity. That is this one. Okay, but you can also define another parameter, which is the fluctuation. So you can decompose the total velocity to an average velocity and a fluctuation part. And this is going to be a cornerstone of our definitions, because that's how we're going to go around difficult turbulence models and basically solve them. Of course, we have defined this as fluctuations for velocity, meaning that's a must. But if you see that fluctuations on velocity, and if you basically conclude this is a turbulence flow, you're going to see the similar fluctuations for pressure, temperature, and even species concentration. Now, let's dive into more in depth into the characteristics of turbulence. See how can we identify turbulence model, or if we put on a step further, how we can actually create turbulence flow. To do so, first we need to define basically what are the characteristics, what are the defining characteristics of a turbulence system that basically distinguishes it from any other unsteady flow. So, one, it is inherently unsteady, meaning it's 3D aperiodic swirling motions, which are, we can call them fluctuations, resulting in enhancement of mixing, heat transfer, and shear forces. So first and foremost is that it is an inherently unsteady. Having said that, as we proceed today, we will see that interestingly enough, we will use steady modeling actually to go around simulating turbulence. But that's a separate subject. We will explain why we will do that, and that's a separate subject. But in terms of its nature, you always consider turbulence as being an inherently unsteady flow. The second one is diffusivity of turbulence, meaning turbulence characteristics can diffuse through your system. Meaning if you start turbulence, if you initiate turbulence at some point inside your flow, it is eventually gonna go throughout the whole flow, diffusing all the corners. So this diffusivity actually is one of the most important aspects of turbulence because it causes rapid mixing and increased rates of momentum, heat, and mass transfer. So this is actually one of the most useful aspects of a turbulence flow. As you will see in our example next week for turbulence, this mixing, this increased rate of momentum, heat, and mass transfer is actually what we want in, of course, many cases. So the next one is turbulent flows are always chaotic, but not all chaotic flows are turbulent. So this is a bit tricky because all of the turbulence flows are chaotic, meaning there is no prediction, there is no way of predicting how the flow is going to behave. But not all the chaotic flows are turbulent. Give you an obvious example. The smoke remaining from jet engines, I'm sure you all have seen airplanes flying in the sky. They leave a trail of smoke behind them. That trail is chaotic because you see there is no specific direction depending on the local conditions and everything else. It can go anywhere, right? But it is not turbulent because it doesn't have diffusivity. If you have noticed or notice it next time you see it, it is not diffusing in the air. Whatever the shape is, it's going to remain like that unless there is a wind carrying it. Remember, diffusivity means there is no external force for propagating the flow. Okay, so that's one example. Or waves in the ocean. They are always chaotic, as you can obviously see, but they are not necessarily always turbulent. They can be turbulent, but they are not always turbulent. So if a flow is chaotic but not diffusive, it is not turbulent. Always and always remember that. Always and always distinguish between a chaotic flow and a diffusive flow. So the next one is its instantaneous fluctuations are random. Okay, obviously we discussed this, but they are unpredictable both in space and time. And that's a crucial understanding because we only explained it in time in our previous graph, but actually in turbulent flow, fluctuations are random and unpredictable both in space and time. So always remember that. Okay, so the fluctuation and randomness and instantaneous nature of these fluctuations happens both in space and time. Turbulent flows are rotational, meaning they have non-zero vorticity. You will see lots and lots and lots of vorticities, big and small, in your turbulent flow. And actually, as we proceed, you will see relying on those vortices is crucial in resolving and simulating turbulent flows. The other characteristic which actually makes turbulent flow simulation much more difficult is existence of wide range of length scales. Meaning you go from very, very small micron size vortices, which we call them eddies. So from now on in turbulence modeling, turbulence subject, we call vortices eddies. So you have from micron size eddies all the way up to, in big flows, maybe eddies that are 1 meter, 2 meter in diameter. Okay, so this makes turbulence modeling very difficult, because in one side, through your proper meshing, you have to solve micron size eddies, and on the other hand, you have to basically solve very, very large ones. So you have to compromise between having 2 million, 3 million, 1 billion cells and not resolving the small ones. So this is another characteristic of turbulent flow. Turbulent flows are dissipative, meaning they basically waste energy. So we'll see later on, but if I want to tell you in a nutshell, turbulence flow works like a system that consumes energy. So it gets the kinetic energy from the system and turns a good part of it to heat, and which heat is dissipated through the wall. So meaning, if you do not keep constant supply of energy to turbulent flows, they are gonna die out. They're gonna slow down, and once they slow down, enough, they're gonna basically turn into laminar flow, or as we say, the turbulent flow is gonna die. So always remember, there has to be a constant supply of enough energy to keep up the turbulent flow. Turbulence is a continuum phenomenon. What does it mean? It means the smallest eddies that define, the smallest vortices that basically define turbulent flow, those micron size eddies, are a couple of order of magnitude larger than the molecular scales. So in no way turbulence is not a molecular scale. Okay, so for that reason we call it a continuum phenomenon. Turbulence is a feature of fluid flow, not of the fluid. So you can't say, or I can't say, water is turbulent, oil is laminar. Such a thing is nonsense, because turbulence is the characteristic of your flow. Meaning, a flow of water can be laminar, can be turbulent. A flow of oil can be laminar, can be turbulent. Okay. Turbulence is very sensitive to initial conditions. Any change in initial conditions, and when we talk about initial conditions here, guys, we are talking about the state of your system at time equal to 0. Your initial, at the beginning of your time, what was the state of the system? That's called your initial condition. So turbulent flow is very, very sensitive to initial conditions, and any change in the initial conditions can alter the flow. Okay, so the criteria for turbulence. So we discussed about different characteristics of turbulence flow, and but all of those characteristics were basically qualitative characteristics. At the end of the day, when you're solving a project, when you're about to perform a simulation, you gotta decide by the numbers that whether your flow is turbulent or laminar. You do that by calculating Reynolds number. As you know, Reynolds number is basically okay, sorry. Reynolds number is basically is a non-dimensional number that relates your momentum forces to your viscous forces. It is your density multiplied by a characteristic velocity multiplied by characteristic length divided by your flow viscosity. Now, in calculating Reynolds number, density and viscosity are of course simple, but be very careful about velocity and characteristic lengths, because these two we call them characteristics because basically they have to be something representing flow, and this becomes tricky when you are talking about the flow that has a wide range of velocities, like from 1 meters per second to 10 meter per second, or you have many larger scale of wide scales of lengths. For example, in some corners of your domain you're going to micron size, in other places you're going to meters. So defining Reynolds number is very subjective, and the advice is you have to basically see what problem you are solving, and based on that problem go look at the literature, see what is the accepted, generally accepted system, generally accepted method of calculation for Reynolds number. So for external flows, for example along a surface or around an obstacle, Reynolds number of more than 500,000 or 20,000 would be considered as critical, which means higher than that number you're gonna go into turbulence flow. In internal flows, for example, flow inside a pipe, the Reynolds number is 2,300. And always remember, Reynolds number inside the pipe is calculated based on the hydraulic diameter. You can find the definition for hydraulic diameter if you Google it, but it's basically a ratio of your perimeter to your cross-section area. So the effect of Reynolds number on different flow, I mean, how would flow change with Reynolds number? Of course we can't exemplify everything, but here I have given you an example of flow around a cylinder. You see at Reynolds number less than 5, which is basically it's called creeping flow. Flow is very, very slow, and the flow sticks to the profile of the cylinder, and that's why it's called no separation, because it's so slow it doesn't separate in this area. If you nudge the Reynolds number a bit higher, between 15 to 40, you're gonna see a pair of stable vortices in the wake. So it's gonna be a bit of separation, and you're gonna see two small circulations here. If you increase it further to just under 150, you're gonna see something called laminar vortex streak, meaning these vortices are gonna detach and move with the flow, but still they have the shape of vortex. If you increase it more, it's gonna be less than 300,000. Okay, it's gonna be laminar bundle layer up to the separation point. So here you're gonna see the first signs of fluctuations on your surface, but still it is considered laminar. You increase it further to around 3.5 million, you're gonna see boundary layer transition to turbulent. Here is called a transient flow. This is neither laminar nor turbulent, so that makes it a bit difficult. Then if you increase it even further than that, you're going to go to a fully turbulent vortex street, but the separation is narrower than the laminar case, meaning you will see something similar to laminar vortex street, but it's going to be a turbulent vortex street. So if we move to the next slide, you will see exactly the same thing in here. So it's basically the same phenomena that you see here with different Reynolds numbers. This is an experiment, of course, and you see it's if you compare it to the previous slide, it's basically matching our result. Now, we mentioned here about we mentioned about the transition. Now let's look at the transition a little bit more. If you are below your critical number, below your critical Reynolds number, you are conveniently at a laminar flow. If you are above that number, you are in basically turbulent flow. But the problem is neither laminar flow nor the turbulent flow, because you know the path, you know the methodology, and you know how to go around it. The problem happens when you're in a transition flow. When you are in a transition flow, flow cannot be considered laminar nor can be considered turbulent. So that makes it very difficult for simulation. And that's something that basically you have to perform a laminar flow for it, then a turbulent flow for it, and then compare the result and choose the best possible result for it.